Hey everyone, good afternoon. I think I'm broadcast. Yeah, there we are. I'm getting some stuff right in the background. I don't think there was extra credit. I know, like, oh, it was just practice. That was just practice right there. I talked to the instructors about adding it on. We'll see right there. I think that might be a good idea to say if you did the practice, maybe give maybe a little tiny. I'll talk to the instructors about that. It was basically just wait for. Yeah. So I don't know. Maybe we'll do it like for the final, just in case people do it. So hey, make sure you do the Proctorio. I think we could do that. I'll talk to them about that. Otherwise, 2 bonus. Does it say that? But we need to do that, and we need to add it on. So sorry about that. We'll put it on there for the bonus too for the final. So we'll be like, because it helps us check to make sure your Proctorio is working. So if it says that, we should probably do that. So hey, great job. Let's throw out some points right there for some people seeing that. Please fill out the Google form right here if you are here. We're going to do a quick analysis and see something. I'm very interested to see this. If you are here right now seeing that in the chat, I want you to go fill out the form, and I'm going to do something real quick right here. I need to subsection this down. So give me a second. I am going and taking the data. We are section 5. Why? Oh, that's the bot, or that's the... Let me go to... Oh my gosh, the text is so big right here. I am very interested, and I want you to see this too. Okay. So I got only our class in here right now. Only our class. Let me make smaller font because this is huge font. Okay, so if you're here right here, let's go to in class. Okay, so 2 seconds right here. I'm getting this. I have the main screen not showing, right? Okay, well, let me see this. I'm not going to be able to see chat here for a moment, but we're going to see who's here. And guess what we're going to do? Is okay if we... Yeah, no, you're just using your name. Just your name. Just your name. Just your name. Just your name. What we're going to do is we're going to do an analysis to see who's in class right now and look at the average of people who are in class versus the average of people who are not in class and responding right now. And I'm pretty certain we're going to see something right here. So give me a second right here as I go through. And I'm going to add this analysis. But how is everyone doing here this morning? Max, Mun, Nathan, good to see you all here. Parker, good to see you all here. I'm going to go through here and add this in and get everything added. So 2 seconds as I do this. Oh, I should have had you put last name first. Oh, no. Oh, my gosh. So 2 seconds. Doesn't want me to change variable type. Change. There we go. Good. There we go. Thompson. But so what are people thinking? I want to come back to the chat and see all this positivity right here. I really believe something. I have beliefs. I have beliefs. Have to do this the long way. We're doing data entry here. It'll take another minute. But do you think... So, Carter, there we go. Do you think the people who are in class are going to have a higher average than the people who are not in class? And I hope this sends out a message because, you know what? I wish I could see if I do something, then other sections. Oh, I think we have someone visiting from another section. Good to see you here. I think, do we have someone visiting from another section? I think we do, which is quite all right. Because I was looking, I was like, where are they in the list right here? And we'll have this analysis done here in a second. The fun of manual entry of data. If you are visiting from another section, say, I'm going to throw 100 points at this person who's visiting, which you are welcome to be here. But someone entered into the sheet a name that I don't have. And so I am unable to add them in right there. We're almost done. We're getting closer to the end right here. Megan, good to see you here. Julia, good to see you here. I am going in. I should have done last name first because I have to reorganize. Daniel, good to see you here. Got Daniel right here. And we're getting close to the end of the sheet. There we go. Shiv, great to see you here. Hunter, good to see you here. Almost done. Nathan, good to see you here. We got a few more names. Lillian, good to see you here. Almost getting down. We're saying hey to everybody. Reed, good to see you here. I am so blind, everybody. Diego, good to see you here. There we go, Diego. Ballin, good to see you here. And Whitson, good to see you here. Oh, last name. Whitson, you're killing me, man. You're killing me. Whitson, you know what you did. You know what you did right there. Is that what you go by, Whitson? I don't know. Maybe you're like, what's so funny, Ryan? What's so funny? Okay. I think we've done it. I think someone might have just entered into the sheet. Okay, good. I think we've done it. Okay, so now let's recode. Oh, we're missing 25 people. What? Wait, is not really? Should be able to sort. Let me sort this descending. Okay, good. Okay, here's all we're missing. Okay. Then I'm going to remove names from this just in case. Good. Let me remove names. Delete names because I'm not going to show it. Delete columns. And, oh, it made it as a new column. That's good. Okay. So let's do this right here. Let me make sure it's pulled up. I have a funny story behind that. Can I ask? Yep, we'll do some exam questions here. I'm mostly happy with my exam. Lost lots more VIF. Yeah, the VIF one's pretty not too tricky. It gave you a correlation, and then I need to close this down. Close that down. Gave you correlation, and then asked you to calculate the VIF. So you need to square the correlation and then get that right there. If you have questions, please let me know. Let me do the analysis right here. You're in class or not in class? Yep, we're seeing it. I can already see it in the data. Yeah, there is a statistically significant difference. Let's go take a look at this. Here we go with some of the data right here. Let's go take a look at the data. Here we go. So taking a look at the data right here, what do you notice about the in-class versus not in class and the grades on the exam right here? Whether you're in class or not in class right now, how do we calculate the R-squared from ANOVA? I'll show you that here in a second. So with this right here, what do you notice right here about the in-class versus the not in class? The highest grades right here are people who are in class. The lowest grades are the people who are not in class. And you'll notice right here that there is a statistically significant difference. Like literally just the people who are showing up right now, the differences we see between the groups is unlikely by random chance. And actually, we can calculate the R-squared from this. How would you calculate the R-squared from this? I ate a granola bar and choking up here. The people in class scored higher. Yep. We see a difference between the means right here. And I'm using jump because it's very quick to do this. So I don't have to load in the data. They're actually 95% confidence intervals. This is a 95%, and that's a 90%, I think, and that's a 95% for the true mean. So those show you 95 and 90% confidence intervals. Yeah. So how do we calculate the R-squared from down here? How can we get the value of R-squared from an ANOVA table? People are wondering about that. How do you get the R-squared from an ANOVA table? The R-squared from an ANOVA table is going to be what your model explains out of the total variation. So the total variation is this down here. So if you add up these two numbers, you get the total. Does that make sense? 105 plus 870 is the total. Does this make sense? 105 is what your model explains. That's the X variable in your model, whether you're in class. I'm doing right, I swear. And then we're going to divide that by the total. And right here, there we go. There's the R-squared up here. There's the R-squared right there. If you have multiple X's, it's going to be each one of the X's. Where do we not want to see? Sum of squares divided by the total. And the way R often reports this, I think, what do we got open now right now? We're doing some 474. The way R often reports this, one thing about R that's a little bit different is it doesn't give you the total. You actually have to calculate the total. I think I have a model currently on here. So if you notice the R-squared right here is 36. In the ANOVA table, it doesn't give you the total sums of squared, which is one of my only complaints. This right here would be the total. And with the total right there, we would take what our model explains. And this is what our model explains. And we can do explains divided by the total of the table and get the R-squared, which you see right there. No, that's all right. That's all right. Sometimes the mathy things, the full grade is not published yet. But we have to go in and grade the interpretation questions, which hopefully everyone, did you have your interpretations on your sheet? Ace those interpretations, get those interpretations down. Don't worry, it just takes practice. Hopefully there's a lot of concepts. Don't worry. Sometimes the more mathy things, like once you see it, it's like, oh, really? Well, this right here if you're looking at this is a totally different thing. And really good question. Should we use the mean or the median for the grades, right? Let me make sure. Oh my gosh, that's worth 100 points right there. Should we use the mean or the medians for the grades? So we want to ask, what was the distribution of grades did it look like? Let's go look at the distribution of grades. And that's the first question. Such a good question. Should we be using the means or the medians for the grades? And we want to get some QQ plots for normality on here. So let's go grab those QQ plots for normality. And let's go look at them. This is why, and we're doing it in jump for a moment. Ooh, what do you think? Yep. I know what we're going to use for this. What would we use right now? And the answer is very clear on what we would use. The answer is very, very clear. Don't look at this down here. Don't dare look at that histogram. Yeah, I was going to use the means. So good, an amazing question. And you can see the difference right here. And that difference of 3.12 right there is the difference between the two groups. So that, and do you think this is pretty practically significant right there? I love what's in with that quote right there. I would say this is a practically significant difference that you're seeing right here, that people who are in class right now, it doesn't mean you will have a high grade if you're in class. Like, there's variation. The highest grade for people, and this is without the interpretations graded, the highest grade currently in class is a 38 versus lowest grade of a 22. The highest grade for people not in class was a 37 with a 19. Both are pretty normally distributed. I know that doesn't look normal, but it does follow the normal curve. And we see here that there's a slightly higher mean of about, remember, that's a 6-point difference because it's out of 50. So it's a whole half a letter grade for just being here right now. Now, that doesn't mean you get it. There's no cause and effect. Good question that came up during office hours. This doesn't mean if you attend class, you will get a higher grade. You can't even see what, Alyssa, we'll look into this. We'll make sure it's showing. Sorry about the list. We'll double check to make sure it's showing. Email me if it's not showing up. And thank you to anyone who emailed me. Whew, last night was a lot of fun. Never give 2 exams on the same day. Lesson of life. Lot of emails. I went for a 30-minute walk, came back and had like 20 emails. And I was like, oh. And that was like I had gotten caught up. If you emailed me last night, I probably emailed you back pretty quickly. Did anyone email me last night and I emailed you back within maybe 5 to 20 minutes? Because I was trying to stay as on top of the emails as I could, because sometimes I would sit back. Like, I sat back one time and I just like took a break and was watching a YouTube video, and I was watching emails go like boop, 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 boop. And I was like, oh my God. Right, Nathan, right? Oh, man. That's when you just stay on top of it. You say, I got to ride that wave. I got to ride that wave. Got to stay up with those emails. I really liked the VIF question. It was a very complex. So whenever you take a test, there's going to be questions that have different levels of difficulties. I just want you to know this, like, the test, a good test, this might blow your mind. A really amazing test would probably have an average of what? A really amazing test would probably have an average close to what? It's how IQ tests work, and then we're going to start doing some material after this. I'll tell you about the VIFs here. An average of 100. And this is not the goal of our tests. This is not the goal of our tests. But I'd say a really great test might have an average of a 50 out of 100. Reason being is you want to differentiate people and figure out who knows the material and who doesn't. Does that make sense? Because what can you always do to a test if you want? If you want, which could, we'll see what averages are. We'll look at things. Instructors will talk and look what was fair and not fair. You want to get a distribution of who knows stuff and who doesn't know stuff. You can always curve it afterwards. You can always, I'm not saying it's going to be curved yet. The instructors are going to look at grades. We're going to get everything figured out. We're going to get grades final live, and then we'll talk stuff. So we can always go back in and shift the distribution. But we want to get a good, like, understanding of what people know or what people don't know. You don't want everyone to get 100. You don't want everyone to get a 0. You want there to be easy questions. You want there to be hard questions. So that way you can figure out to what degree people's knowledge are. The final is kind of cumulative because it stacks on the knowledge. You're not going to need to know, like, some people were saying, like, oh, I didn't know how to calculate a discrepancy. Anything that is mathematically related, like, here's tips for the final. Anything that is mathy, that requires equations, what should you do with those? What should you do? Which, these are tips for the final. And, like, it's hard, like, I can't be like, hey, this is going to be a question that tells you to do this. But anything that's mathy, what should you do? Would you want a median? You could, yeah. Cheat sheet, put it on the cheat sheet. Like, if you're like, how do I calculate the R squared? So remember, the R squared is the percent of variation explained. So an ANOVA table shows you what's explained and what's not explained. So knowing the values from the ANOVA table to calculate, and then just practice and write it down and have it on your cheat sheet. So let's look at the VIF and how that works, because VIF is very important for multiple regression. Let's look at some VIF. So when we have a VIF right here, this model will not have VIFs because why? Why does this model... Oh, well, we didn't put a model in there. Why is my model not giving... Well, it literally says the answer to it. Why is my model not giving me VIFs? What's the point of VIF, and why does the model not give variance inflation? The answer is here, and then the code is telling us the problem with the model. So we're going to remake the model while you think over. It's how does our x's explain our x's? And so to kind of talk about, I'm going to kind of do a very similar problem to what was on the test. I thought it's really such a great problem. Probably one of the tougher problems, but if you know what you're looking for, it's not a tough problem. But like, it gives you extra information, which always makes problem tougher. If we're looking at height, weight, GPA, and so now if we know what VIF is, stop at a moment, we'll calculate the VIF right here. Okay. So here's a model, and let's calculate a few things. Your problem gave you stuff like this. Give you core. I think core will get it for us. I use core test. Core test does it also. It wants height, comma. Oh, well, let's use core test then. Core test does it. Really? Oh, it doesn't use data. So many codes to remember the order of. There we go. Okay. One of these will be important for VIF. Only one of these. Okay. Which of these is important for VIF and why? Which of these is important for the VIF and why? Who knows which of these is important for the VIF and why here? Which of these is going to be important for the VIF and why? Take a moment and think it over and be like, why would one of these be important for VIF? VIF stands for variance inflation. It's the overlapping multicollinearity between the x's. So it's a bad thing in multiple regression, which the remainder of the class is on multiple regression. So which of these is bad? Well, so correlation can help us find something else. So which of these is going to be important for the variance inflation, which is the shared variation among the x's? So if you had a question like this, you'd be like, wait, this looks like last night. I got 3 correlations, and which might be able to find the core just alone. Which of these would be important and why? The first, the second, or the third? VIF tells us the shared variation among the x's. Among the x's. Which of these would be important and why? VIF tells us the shared variation among the x's. Who knows? 100 points in the chat. Who knows? The third. Why is the third correct one? Why is the third the correct one? Why is it the third? Because I'm saying it. VIF tells us the shared variation among the x's. Among the x's. So this value right here is correlation. And how do I get r squared from this? To get r squared, I simply do r squared. So everyone... Oh, I think I'm taking the... What? Hold on right here. Really? R, you're being weird today. There is r squared. I have no idea why I did it like that. It hurts my brain. Does anyone know the equation for VIF? Another 100 points in the chat. What is the equation for VIF? Hint, this is r squared now. Among the x's. Ah, no, that's going to be the error. 1 over 1 minus r squared. I realize, yeah. And there you go. And that's the VIF. And here's the thing. This is probably one of the toughest questions on the test. Like I was looking over the test, seeing what people missed. That's probably one of the toughest questions right there. It gives you multiple things. You have to know to square it. Amazing work. 100 points in the chat. If you got this question, great job. You probably got one of the toughest questions. Oh, you did 1 minus r squared over r squared. Here's the thing. You gotta use your formula sheet. Don't worry, like in a good way, Mun. 100 points, Mun. Use that formula sheet to your advantage. Have written down 1 over 1 minus r squared. But do not worry. If you made an 80 on this test, that's really awesome. Dr. Petrie used to like to say no one makes 100 on his tests. I think the only person who would make hundreds on Petrie's tests, I'll just say this much, my tests are not as hard as Petrie's tests. Petrie's tests are, woo, we take a Petrie test. Woo! I took some Petrie tests in school. It was a tough test. I know a person who made 100 on Petrie's test, and they're currently doing a PhD in computer science. And they also found 1 error on Petrie's test. And he's like, yeah, they found an error. They're really good, and they're doing a PhD at UT in computer science right now. They're super. I mean, like, I've met smart people. Nothing against anyone. Nerd alert. Hey, I'm proud to be a nerd. I'm a nerd too. Oh no, I didn't make 100. Petrie's test will throw me for a loop. He would have me take his tests. When I was Petrie's TA, he would have me take his tests for these class. He would say, Brian, I want you to take this test and see how you do. So then it's like I'm being tested as his TA to see how I do on the material. And he'll write trick questions. It's tough. So don't worry if you didn't make 100. If you made a 90, wow. If you made an 80, that's great. If you made a 70, that's all right. If you made a 60, we're going to try to raise some grades here. Pretending. I think, because that's the goal, kind of, is you always want to challenge people, Kevin. No, great question, Kevin. 100 points, Kevin. You want to make it so that your exam is challenging enough that there are questions that push everybody. And you always want to challenge students. Because if someone just walks through your class and knows the answer to every question, then the class was of no use to them. But if you can find gaps in people's knowledge and challenge them and grow what they know, that's what we like to do. So it's not like no one passes my test. And then it's astounding when someone gets it all right. And you're like, wow, you knew it all? I couldn't stump you in any way? Maybe it's like a competitive thing too, to like try to stump somebody. And when when students work really hard, and don't worry, like, I think your hard work pays off in here and it's showing. So we're gonna head back to the main screen. Now, I really like this. A lot of people were saying this. They were saying the take home was easy, and I like that. So the take home, I think, was the easier portion. So on the VF question, we needed the correlation between the two. Exactly, Nathan. Yep, because variance inflation is the shared, but the multicollinearity between the x's. So the correlation to proper correlation to choose was the one for the two x's in the model. Oh yeah, no, it was a tough exam. It's a tough exam. Tough exam. Use that note sheet to your advantage. Use your note sheet to your advantage. No, but I'm really proud of everybody. Grades are looking pretty good. Do I have all sections? I'm going to do something. I want to know how we did compared to sections. Who wants to know? Who besides Brian right now wants to know? And then we're going to get serious here with topics. Who besides Brian wants to know how our section did compared to other sections? Did I already delete that sheet? Who here would want to know how our section did? Oh, come on, section. Okay, 2 seconds. I want to know. Let's take a look. I really want to know. Okay. We are section... I like it. Does it have the bot in here? Well, I don't think we can count these zeros. I don't think people made zeros. Redo. Automatic recalc. I'll show you here in a second. Was it not? Oh, I have to remove the rows. Rows, hide and exclude. We are section 5. And if you're wondering, let me close out this sheet. Don't save. No, don't save. I have to keep that open. And so here is the analysis. We are section 5. There's not a statistically significant difference. Let me run the connecting layer. I'll show you this in 2 seconds. There's not a significant difference, but I'll take it. There's not a significant difference, but I'll take it. Here we go. Let's take a look at it. Only 3% of the variation can be explained by the class you're in. But not a significant... Oh, you see, I think some people have already had their things graded. Some sections have already have a little bit of the grading done. So if you notice here, why certain grades are a little bit higher, some sections have already... A few of the interpretations have been graded, which that's why you're seeing that, because the highest you could get was something like a 44 or 42. But we are seeing right here, here's our section 5 right here, which I'll take it. I'll take it. So that's fine by me. Grades are looking pretty good. We're not seeing as many low outliers. Good right there. Yeah, then we'll see after it's all graded. So we'll have to wait for everything's all graded up. Only 3% of the variation. There is no statistical significance, which is good. And I'll take it also because, one, my class is all online. hey, if we're doing just as good as everybody, I'll take that. But I'm rooting for us. I love all students, but come on. I want my students to do the best. That's what I always want right there. I mean, come on. What person says we're clearly... No one wants to be an influential point in the model. And you can see it's, look at these normal distributions. If you see how these are spread right here, more variation in this section. This is the section with the most variation in it. Very interesting. But it might also be because some of the things are graded. Okay, so that's got it. Let's go back. Do we have an outlier? I mean, the distribution is normal. So no one's really an outlier. There was not anything extremely far away. Most of it's normal variation. There might be some that are a little bit low, some that are a little bit high, but most of it's normal variation. So love analysis of data. Analysis of data is awesome. Let's get back in here and start talking about... Thank you, everyone, for being here. Chelsea was telling me how, like, people she works with were talking about, like, oh, I don't like statistics. Oh, statistics, that was, like, the worst course ever. To me, statistics is about telling stories with data. I love statistics. You probably couldn't have guessed that. But statistics is about learning about how to describe the world with data, and you get to tell stories. It's about what does the data tell us? What does it mean? And yeah, to me, it's about knowledge. Knowledge is power. So what do we try to do? We might still see, we'll try. Once again, nothing against any classes. But if you ask me, Brian, you get to pick which class has the highest average. What class do you think I'm going to pick? So I want all classes to do well, but I want us to do great. Statistics is about creating 3D... Witty, no. No, 100 point. Don't be making those 3D pie graphs. Don't you do that. Don't make a 3D pie graph. Please don't. Let's go to the main screen. You know what? Here, wait, 2 seconds. You're just throwing down some great quotes. You now have another MuBot quote right here. For future classes to see, quote 114 is now statistics is about making 3D pie graphs. Please don't ever make a 3D pie graph. Quote 114 in the record book. So let's hop back into this right here. So what are the two things, and this is for the final now. This is all stuff for the final. What two things do we need to know about a point being influential? When points are influential, what will cause a point to be influential? Is there a quote zero? I don't think there's a quote zero. Is there a joke zero, but not a quote zero? Maybe there's a quote zero. What two things will cause, the best thing to do is think about a simple model right here. And we have a lot of these graphics coming up. I can show you them, but let's draw it out. What two things cause a point to be influential? Leverage and deleted studentized residual. Witty right there. I'll call you Wits. No, that's Walden. Serious face. So what is leverage? Leverage is on the x's. This is just a simple model again right here, where the further are you away from the mean of the x's, the more leverage you have. You can think of it like a seesaw right here, and the mean of the x's is where we're balancing on. So the further you are away, the more impact you're going to have on the model. But this point right here would not have any impact on the model, even though it has extreme leverage. Why? This is a review right here. Why? This point, I love it right there. Filtering out the ghost. This point is not influential. Why? That point actually just kind of is like a nail in the model, nailing it where it's at. It's not influencing the coefficients in any way. And that's what we mean by influential. It's on the line. Nathan's got it right there, which means it has a deleted studentized residual. Wilton right there, very, very small, next to 0 deleted studentized residual. Please review last class. We've got the videos marked and everything, going over these topics and how we can calculate something's leverage, which is the unusualness in its x's. This is not a y and x graphic. This is the unusual nature of something in its x's. Combination of x's that are unusual give points high leverage, where points being far away from the model would be a large deleted studentized residual. And so deleted studentized residual is when we calculate a line without this point, and then we calculate its residual from that line without its influence, which generally makes it bigger. Deleted studentized residuals, very easy questions for the final. Deleted studentized residuals are more extreme in absolute value than what? Deleted studentized residuals are more extreme in absolute value than what? A deleted studentized residual is more extreme in absolute value than what? In absolute value. It's basically your 6895 too, because 95% of the time a deleted studentized residual by random chance would be contained within 2 or -2. That's all we're saying, is what would we expect normally is within -2 and 2 for things to fall in this range, and something right here that's outside of this range would then be unusual. Let's review. Please slow me down if I'm going too quickly. But when we talk about leverage, and I would put this on my formula sheet, I highly doubt, I'm not a big fan of this sort of question, but if when we want to calculate if something has high leverage, K is the number of predictors in the model. I do not solve this out by hand because this equation right here, and I'm going to put it with a red arrow. Where is this equation? Ooh, it's a good question. Good review. Where is this equation being visualized in the following graphic? Think about this. This is the point at which we have high leverage. It's a calculation being done for you with the amount of predictors you have in the model over the amount of sample size, a little math on the amount of predictors, 2 times the amount of predictors plus 1 over the sample size. That is being shown to you where on this graphic. That numeric calculation is where high leverage is, and that would be where? Where would that be on this graphic? Like, where is that calculation being done for you, showing you the point at which something has high leverage? What maybe is that calculation? Like, what did it calculate that to be? Although that's where deleted studentized residual is. So Nathan, that's where, yes, this is where the point at which high leverage is. Great answer right there. That's the high leverage point. That is the equation you're seeing right here doing the calculation to tell you where high leverage is. Does that make sense? No, good. That's where high leverage is. High leverage is calculated and shown right there. Anything down here, be very careful. Good theory question. The points down here would all be very close to the where. Where would the points down there be very close to? Think of this. They have no leverage. The points down there would be very close to where? They have very little leverage. Max, you are 100% right. That's where the mean of the x's would be at. That's where, because they have no leverage. They have no leverage. Now, they could be far away from the model if they're up here somewhere, but they have no leverage if they're down there. So it's a little bit confusing because your model's kind of like folded over on top of itself. It's like you took and folded over here, and anything further out here has more leverage than anything further out here. So this point over here could actually be a point. It has to be below the model. It could be down here somewhere. Does that make sense? Theoretically, I think that's where people usually get confused on this, that this could be this point that I have circled over there because it has high leverage and it's decently below the model. The model being going through here. So you would take and fold the graph over on itself because anything at the mean of the x's would have zero leverage. So little bit, this point right here. So it has good leverage. Does that make sense? It has leverage and it's below the model. But remember, leverage is a positive number. Does that make sense that leverage can only be positive? Something on the mean of the x's would have leverage close to 0. So something right around here has leverage close to 0, but as you go further out, leverage gets more extreme. Something down here would have a leverage of 0. As you go further out, leverage gets more extreme. The graphic you're seeing right here, got a lot written, is only showing how big the leverage is, but the further it is away from the mean of the x's, the more leverage it has. Does that make sense? I think people point tortilla. It's like a quesadilla. Yeah, it's like a quesadilla. Like if you think of it that way, that helps. But so little bit, I think once you see it, like if you see it, like, okay, we're taking and folding this over and we create like a tortilla right there. We got Los Dias de Muertos coming up here on November 1st and 2nd. Happy Los Dias de Muertos. So this point right here, if you have a model, that point, there's the mean of the x's. Kind of, I like to draw as a little seesaw right there. You got a whole bunch of points over here at the middle of this. And then you got a few high leverage points somewhere out here. That point is to be below the model, so it could be over here technically. And remember, we would take and fold this over right here. And the point, exactly. The things on the average are going to be the high, yeah. And if you think about the center of your tortilla, then that's going to be like things that have a small deleted studentized residual. So like literally, oh, it's such a good way of talking about it. If you fold this over right here, the things right here, I wish I could bring tacos to class and then we could do this. Does that have high leverage? So when you fold over your tortilla, does that have high leverage? Yes, but it has a small deleted studentized residual. I guess we're actually folding this way. Gotta fold my tortilla right. So it'd be on the model. So you're gonna fold your tortilla that way. You're gonna be weird. So that's on the model. So when you fold it, yes, and then something over here, this right here has, it's far away. Does that make sense right there? It's on the edge of the tortilla. So that right there, when you fold it, you're actually going to take and fold this over on this side. So something over here would have the same amount. Does that make sense? That would be of the same influence. Does that make sense how that's this? I think this is a great example right here. Does it make sense that these 2 points, point 1 and point 2, when you fold this over like that, they're going to have the same influence? Because they have the same distance away from the model and they have the same leverage. So leverage is the calculation. They both have the same leverage. And then deleted studentized residual is your kind of y distance. Yeah, and so they're going to have about the same the way I drew it. So that deleted studentized residual right here is going to be very, very similar. The deleted studentized residual is basically this right here. I thought I changed colors. The deleted studentized residual, which we really, great job right there. We really only care about the absolute value of it if it's outside of 2 or negative 2. And it would be calculated there on its y distance. Does that make sense? Good theory stuff. So the tortilla being folded over is, everything's food references. That's going to be down here at the 0. And then we have a point at which there's high leverage. So we'd say certain things are going to have undue high leverage, which would be a marcation right maybe here, which it's on the same thing. So when you fold these over, which if I draw this properly, does that make sense? When you fold it over, that the high leverage, as long as I did it symmetrically, the idea of high leverage is the same distance away, whether positive or negative. If you fold that over, you're going to see right here. So there's the tortilla at the center. We fold it over this way, and you'd get this right here. And then the points that are below are still going to have high leverage. They would just, leverage is a numeric or a calculation of how far you are away from the mean of the x's. So it doesn't matter, Rock.
It doesn't matter.
If you're above or below the x's, you still have leverage on the seesaw. So you'd still have leverage down here as you still would have leverage up there. So many colors. We love it. We love it. We love it.
Wow.
So what is this reporting to us right here? This is reporting to us the rows with high leverage. These are the rows with high leverage. Do you think this model has too many points with undue influence? Do you think this model has too many points that are like, yeah, that's a lot of points with influence? These are the points that have a lot of power on our model. We don't like that. What do we want? QQ straight enough, no outliers. And moreover than these being outliers, because something could be an outlier kind of in like an extreme sense on one of the values, these are points that are pulling the model towards them in a very strong way. And with this right here, the influence is actually the size of the circle. So the bigger the circle, the bigger the influence. So what's really interesting about this, if you notice kind of the specifics, there are some points in here which we are not reporting. What do you think about these points right here that we are not reporting? Those were not reported, but what do you think, since you now know the size of the circle is the size of the influence? The way we've done this calculation right here, what do you notice about that? You'd be like, oh, the size of the circle is how influential they are. And what do you notice about those points right there? And they just barely did not have enough leverage for the way we do the calculation to be reported. What do you notice about those points right there? It's like, ooh, those points really have a, ooh, uh-oh. Looks like we got more problems than we thought, right? Because those are not being reported. The ones with the X's are being reported that fall inside of these two regions. The region up here, let me change color. This region up here is a bad region, bad. And this region down here is a bad region. They have a super great job right there, Max. They have such a crazy deleted studentized residual. They're very influential, even though they didn't come up. They didn't have enough leverage. They're super influential, but via the way we do it, they just barely didn't have enough leverage to be reported on. If you notice, they're right on the edge of it. The center of the circle is somewhere just barely outside the bad range. So, but they do have a lot of influence. Frankly, we probably have more influential points than are even being reported. This model has too many points with undue influence. I'd be wary about using it. Here's how we can get the reports on it. We can just add in the rows right here. This is your data frame with the row space. So good idea. Once again, review. You don't want to just toss out points unless they are literally points you wouldn't report. Who knows how to do extrapolation? Let's take a vote right now. Review extrapolation or don't review it. Let's put a little chill music on right here. Review extrapolation. Don't review extrapolation. Yes, no in the chat. It's the votes appearing. Who thinks they know extrapolation? We have a code extrapolation check, and it is shown throughout the notes how to use it. You vote now. Review extrapolation. Don't review extrapolation. I will do exactly what you say. We'll do 10 seconds on the clock. All people are saying yes. Yes is winning out. I will review extrapolation. You're here. You get to choose the way the class goes. Yes is winning out unless there's a sudden surge of no, don't do extrapolation. Let's talk about extrapolation. The key word right here is extrapolation. Now, it's very easy to think about extrapolation in the univariate sense. The univariate sense makes it really easy to understand what's happening with extrapolation. When we talk about extrapolation, this point down here is very what in its x sense. Like here's our x's, and here's kind of the eigenspace. I just love that word. It's the orthogonal space. And what do you notice about that combination of x's? This is not an xy combination anymore. Yeah, do you want to review it? Maybe I reversed it. Yes meant we want to review it. And we can slow down if people think I went too quickly. What do you notice about this starred value right here? It is very what? Far from the mean of the x's. So that is what we're seeing right here. It's very unusual in its x combination. And so I think a lot of people sometimes think, wait, isn't this a y and an x? No. This is an x1, x2, because please put in the chat for 100 points. When we're extrapolating, we're going to extreme values of what variable in our model. When we are extrapolating, the model is trying to make predictions that are very unusual or outside the boundaries for our what variable in the model. Since we're looking at x right there, Hunter, you got it. So it's on the x. Why does x1 and x2 mean, though? Yes, exactly, Nathan. Yep, you're 100% right for another 100 points. It's just a theoretical x1 variable for your model, x2 variable, where this has a very, very odd, that point we circled right there, has a very odd x1 and x2 combination. So the model is actually going to have a lot harder time predicting this than it is points towards the mean of the x right there. So how can we actually check into this? With extrapolation check. Extrapolation check is going to tell us how far away things are from the mean of the x's. If we were to run an extrapolation check, if I were to check this point right here, what would you guess that point would come back? If I run an extrapolation check on that point, what do you think it would come back as? You know what? Let's see that. Let's go run this. Who knows for 100 points? What do you think that would come back as? So we've got a model already. And so here's our model. We're predicting somebody's height from weight and GPA. Could you predict F for given value Y, or is that not something? Mm-hmm. Oh, wait, no, we wouldn't predict X. The model's meant to predict Y. We could switch X and Y and then do that, but we predict Y for a given value of X. It's just X is explain why something is happening. We predict Y. We predict why something is happening. So let's go here to data frame, data.frame, and let's go right here. And let's go to weight, or yep, there we go, equals mean of survey $10 sign weight. And GPA equals, I am making a data frame of my what's right now. This is important theory. Brian is making a data frame with variables of his what right now. To do the extrapolation check, you need a data frame with your what's in it. You could put more. Let's go crazy on here. Let's do a second value. To do extrapolation check, this is what you want to write down. You need a data frame with your what's in it. This person is going to weigh 400 pounds. And this person's going to have a GPA of 0. I think I have my commas right. Looks like I do. I'm making a data frame with my what's in it. To do extrapolation check, you must have a data frame with your what's in it. To do extrapolation check, you must have a data frame with your what's in it. To do extrapolation check, you must have a data frame with your what's in it. What are these from my model? To do It doesn't have to have the mean of the x's. It just has to have x's in it. 100, good answer right there. It doesn't have to have the mean of the x's. It just so that's why I added more. You don't need the means in there. You just need x's, because what are we going to check? We're going to see if to predict for this person right here, if we would have to extrapolate our model. Does that make sense? What extrapolation check is going to do? It's going to say, I'm going to try to predict person number 1. Does my model have to extrapolate? And basically, how far out in my x's do I have to go? Now, since that person, and extrapolation check, oh, do I not have? There's extrapolation check. Takes the model and takes the new data. Good. Now, let me ask you, that should work. Got new data as that. Let me ask you, since this person's at the mean of the x's, how far out do I have to go in the cloud of data to get to that person? Since this person here is at the mean of the x's, how far out do I have to go in the cloud of data by going out a cloud of data, like going and going, how far out in the cloud do I have to go for that person at the center of the cloud? How far out do I have to go? 0. That person's not an extrapolation of the model at all. They're at the center of the x's. And then this person over here is extreme. So how far out do you think I need to go in the cloud? Which this is similar to our example. This person in my model weighs 400 and has a GPA of 0, which is very far away from where we'd expect people to be on their x values. So what do you think that someone very far out on the cloud would get? Who's very extreme in their values? Very unusual. The more unusual you are in your values, the more you will go towards what for the percent of data we have to go through to for your x values. The closer this person right here, when I do the extrapolation check, will get a value of what? Another 100 points down. That second person will have an extrapolation check value of 100 points in the chat. Not one. I mean, not one though. Oh, model M not found. Oh my gosh, model M. 100. Why is it 100? I just want you to think, why is this person getting 100? Now, it's similar, like this isn't the exact same graph we're using, but why does this person get 100 right here? What does it mean that this is the 100th percentile? What does that mean? Yeah, you're seeing it right there. You're seeing it, Max. Yeah, Max, great job right there. You're seeing it. The person at the center of the cloud of the data, you've gone through 0% of the data to reach them, where this person is at the 100th percentile, meaning you have to go through 100% of the x values to get to them. So that would be where you'd be extrapolating to help with this person. Yeah, so no, like I was like, when you said 1, I was like, if you're going through like 100% of the data, 1. Yeah, so it does report it as a percentile though. And that's what extrapolation check is doing. If you look at this point right here, this is going to get back 100th percentile for that point. This one might be about the 70th. This one might be about the 94th. And when we run the check right here, we would put in the x values for those individuals. It was close. This one was the one I got wrong. This was the point I said would be about the 70th. So does it have to be... generally, we don't like to see things around like 95th percentile. It's the further away you are. Whitson, great question. Like this one is fine. This is fine. Everything's fine. This is bad. This extrapolation has a degree. Because the further you are away from the mean of the x's, the more you're extrapolating your model, because the model will have more uncertainty and do worse and not be based on data that the model was created around. So when you're going further out on this, your model is super bad on this right here. Like this is horrible. Over here is kind of like, okay. The model can happily predict inside of here. I should do those in different colors. But does that make sense right here as we think about how the model does extrapolations? Right in there, the model's super happy. Over here, the model's like, I don't know about that. But out there on that extrapolation point, which was at the 100th percentile, the model is like, no. What are you doing? This is a bad idea. Does that make sense right here? That frowny face is where we are extrapolating our model, and our model really doesn't have data to tell us what we should expect for those x's right there. Where the so-so face is like, yeah, you're on the edge of your data, because that so-so face right there was where we're doing the bad right here. And you really want to think about these as a matter of degree. Like the model's happy to predict right there, and the model should not be predicting over here. Everything's all matters of degrees. Exactly. All models are wrong, some are useful, and some of these ones are happy. I like that right there. You always want to think of these things as like, it's never bad. It just gets worse. All models are wrong, and your model right here is going to be, help you with a little bit of an extrapolation right there. A little bit of extrapolation. Don't do that. When it comes to variable creation is basically just making new variables.
Wow.
Making new variables means we're going to take our previous variables and put them into some combination. Pretty easy, and probably is one of my favorite and easiest parts of assignments when we do it. You just take variables and put them together. I've worked with so many people. I'm working on a veterinary thing right now, and we're taking certain variables and finding combinations of them, like certain heights and weights. We're literally doing stuff like this right here, measurements on animals, and then creating new variables from them. Because maybe you're interested in like a density, or you're interested in like a ratio to see like, if you have something that's bigger, you would expect more from it. So we want to see like compared to the size, how much of this is there for the animal. Literally what I'm doing. And I love it when I'm working with somebody on their research or something, and they say, maybe we need to create a new variable. And I'm like, I teach that. And they're like, well, yeah, you need to know that. So how do we create a new variable right here? Well, this is a Kaggle competition. Check out Kaggle if you have not, where if you use how many variables? What's going on right here? How many x's were used in this model? Who knows what this means? How many x's did they use? How many x's did they use? How many x's did they use? All of them, all the x's. So you might say, well, wait a minute. If I use all the x's, I'm stuck. No, there's a lot more you can do. There's a lot more you can do. What they actually did here was, and their R squared is 62%. Let's look at the model. Plot 1, plot 2, plot 3. Where do you see the problem with linearity? Plot 1, plot 2, plot 3. Where do you see the problem with linearity? Don't make me sad. Don't make me sad looking at this right here. Where do you see the problem with linearity? Well, so specifically plot 1 though, right? Plot 1, this is the linearity right here. That's the linearity of plot 1. This right here is a problem with the what? How it disappears. Oh, it doesn't say it. Doesn't say it, but it should. I think it's just cut off. This right here is a huge problem with the normality of the residuals. Don't look at that. Don't look at that histogram right there. Don't ever look at that histogram. Don't you dare look at that histogram. Don't mind if I do. Homer Simpson right there. It looks good to you. Whitson, you kill me, man. So what have we done right here? So the screen. We've created a different model right here. And tell me, when you look at this model, what immediately jumps out to you about this model right here? What immediately jumps out to you about this model when you're like, ooh, that's a good model? This is a model that won $5,000. It's a good question. I've deleted it off before. I've deleted it. Like I can remove it from the check regression. I can maybe show that here at the end of class. You can remove it from your output to tempt you. It's a good question, though. It's because Petrie created the code with the histogram. You can recode yours to remove the histogram, though. It's not too bad to recode to remove it. So what do you see right here? Like you look at this output and you're like, ooh, what do you notice? Should see something in this output. You're like, wow. Owen Wilson saw it.
Wow.
What do you notice in this output right here? Yeah, that R squared though, right? That R squared is ridiculous. And this is a one variable model with the variable created. Please note that we have created a new variable right here, which is the log 10 of sold week 26 right here. All this is being created right here times Z. Z is this other portion of it. And so this is a new variable being created right here. So here's the Z new variable. So the new variable is being created right here. We're pulling it from the data frame, so we're not using the data equals because this is pulling it from the data frame and the Z from the global environment. And R squared is on steroids, I do agree. Now, but let's look how the model does. Ooh. Looks like we fixed what issue most part, though. Now, I know this does fail. I know that does fail. But I would say we probably have a much more linear relationship, which is kind of one of the key assumptions for linear regression. So I'd say we're doing a lot better on the linearity, but over here, the normality of residuals might work worse. But here's the thing. I'm not even joking. You might say, well, 98% R squared, normality of residuals, whatever. Your model's not going to be perfect. Why do they do log for their Y of the variable model? What does that do? Log will pull in extreme values. So with extreme values right here, if you have extreme values, The log will try to create normality, and a lot of these algorithms work better on normality because extreme values will pull the model and create like influence on the model. So creating like logging variables often creates normality. So it's such a good question, Max, right there. Log is a very common transformation for extreme values to pull them in and to create more of a unimodal normal shape to it. So why would we log something? Well, we could try different power transformations, try like a series of powers and see which works best with like fine transformations. And then whichever power works best, hopefully we maybe pass conditions a little bit better. But in truth, even though there's problems like the normality of residuals, like this is like the super bad one right here. This is fine. Little smirk in here. That one's smirking at you right there. The linearity and the equal spread, I'm not so worried about. Yes, there's a problem with normality of residuals, but you know what? That 98% R squared, I'm going to take this model. And this model literally won $5,000. All models are going to be wrong. Every model you ever create is not going to be the truth. We're here trying to find the truth. Here's the truth. Your model did a pretty good job. It still has problems, though. So when we do this right here, important notes right here. If you're creating a custom variable, here are the steps. Creation of custom variable. Please take a note of this right here. If you ever have to create a custom variable, 1, store your new variable to the global environment. 2, store your variable into your data frame. 3, create your model. Nathan, good question. Probably domain knowledge, like maybe they know stuff about how stores work. So a lot of times the creation of these variables, like when I'm working with veterinary people, they're saying like we should do this or this. This is what the literature says. So it requires a lot of domain knowledge. What does domain knowledge mean? Like, how would you know what to do for this? Well, you probably work in these stores. And you're probably like, well, we usually see this, so we should maybe look at the ratio of this to this. So that's the hardest thing. Like, what statistic in baseball has recently been created that is a super important kind of variable creation? I think it's variable creation, right? I think it'd probably it'd be a variable creation. Yeah, because the first thing is a this above something else. I think it is above. And so it's like is it a ratio how they calculate it? So you probably know which statistic I'm talking about, and that's the idea of a variable creation. So they take two things that exist and then they make a new variable out of it. Exactly WAR. Wins above replacement, is it? I think it's wins above replacement. Tell me if I'm wrong on that. And so WAR is going to be the idea of a variable creation. And literally that didn't exist. You go back 10, 15 years ago, no one's going to have the WAR statistic. You say, well, what's the WAR? And what are you talking about? And so wins above replacement. Yep. And so that statistic right there is very useful and is great. Like, how do people care about that, Whitson? Do people care about the WAR? And you'd have to calculate it from your data by creating a new variable. If you already have someone's wins and replacements, I think I haven't calculated it myself, but you would need to create it, append it to your data frame, and then use it in a model. And that is a very, 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 very popular statistic these days in baseball. Mike Trout got the biggest contract in MLB history entirely because of his WAR. Talk about an important statistic. Is he the one who also does analytics? We reached out to someone, he didn't reach back. EPA is super cool in football too. Yeah, there you go. I don't know what EPA is. I know EA Games, but I don't know EPA. EA Games. It's in the... Oh my gosh. EA Games. It's in the... Why can I not finish the saying? Wow, my brain is broken today. 426 million, almost $500 million. It's in the game. It's in the game. EA Sports. It's in the game. Oh man, why did I not, Kevin? Thank you, Kevin. My brain broke on that. EA Sports. It's in the game. How do you not know that? Okay, what is a polynomial model? Who knows what polynomial models are? This one, when you think about what a polynomial model, EPA expected points above at a base. Oh my gosh. Yeah. New statistics, better statistics. What are these polynomial, too much FIFA. What are these polynomial models going to allow us to do? This is one of my favorite things we cover. What are these polynomial models going to allow us to do? What is a polynomial model going to allow us to do? What can we do with polynomial models? What will a polynomial model allow us to do? Any ideas? We can look at non-monotonic. Monotonic means goes in one direction. These are monotonic. Monotonic is one direction. But now, with polynomial models, we can do things that don't go in one direction. I mean, they can still go in one direction. That's one direction. But now they can go up, then down, and they also don't need to be aligned. Non-linear, more flexible. But wait, could we fit something? Hey, wait, count with me. I'm not going to say. What degree polynomial is Brian drawing right now? Okay, I think, what degree polynomial is that? I think I know what it is. Who knows what degree polynomial it is for 100 points? Who knows what degree polynomial? Can I fit that through my data? I can, actually. I could fit that. Is fifth degree polynomial correct? This is second degree, third degree, fourth degree, and that's a fifth degree up there. You can basically do bumps minus 1 if you want. So 1, 2, because it gets its first bump when it becomes a second degree. And so the more polynomial you get, the more it can kind of bend through the data. That's what we do. So the question becomes, what do you think your question is? When it comes to fitting a polynomial, what are you wondering? What are you going to have to decide for that polynomial? Because you could, and let's repeat again, you could do this, you could do this, you could do this, you could do this, you could do that. What do you have to decide? What are you going to have to decide for your data? What are you going to have to decide on for your data? Just talk to me words. This is all the mathy way of talking about it. But explain to me what you're going to have to decide when you make polynomial models. Like, if I make a polynomial model, I'm probably going to have to decide this for it. What are you going to be deciding? It says it all up here. But you're going to be deciding, and so what's the order? How many bumps there are, right? Like, how much bendy allow am I going to give? That's grammar. Check it out. And I absolutely love this code. It's one of my favorite codes just because it makes such beautiful graphics. We know that a relationship exists between height and weight. Would it make sense to you that there is a relationship between height and weight? Like, just, I'm going crazy right here telling you that height has a relationship with weight. But you notice over here at the end that there's a bit of a linearity problem. So how about we do this? Choose order. Now, this only takes simple models. And take a look. What color graphic do you think we should use right here? Your eyes are probably telling you the best one to use by just looking at this. It is iffy, though. Actually, yeah. It's really interesting. I know, right? That it goes through and it fits polynomial models. If you want to see something even cooler, is it max order? Sometimes I forget. Yep. There you go. I love this code. There you go. But you notice, I don't think we're getting much out of this after a certain point. Do you see how I don't think we're getting much out of this? This is a polynomial to the 20th degree fit. You can choose a higher order. You can fit, let's see what it does. Let's do this. Yeah, it said no. It doesn't have enough, it can't fit the polynomial terms. Yeah, we hit right near the top, didn't we? Ooh, is 20 the highest? Really? Apparently. Maybe it just is. Team green right there. You going with team green? Well, there's more green now, right? So let's go back down. Let's go back down to like 6 again. There we go. Green and red are pretty good. But what's very interesting is there's this little dip right here. And I'm going to have to zoom back in so we can see output and read numbers. Let's remake the output. It'll resize it. The answer to this question for a test is the following steps. Are you ready for these steps? Write these down. This is just like your check regression, as in you need to know these steps. Here we go. Step 1. Find highest R squared adjusted. Why are we using R squared adjusted instead of not using R squared? Why are we using R squared adjusted and not R squared? Why is this adjusted and not R squared? This is a great theory question. Relates to the last test. Why are we doing R squared adjusted and not R squared? Why are we doing R squared adjusted and not R squared? Why? Because exactly, we're adding in more code. Because every time we add a polynomial term, it's another x in the model. It's on the same x, but it's a polynomial of the x. So since this is a multiple model, great job everyone right there. as we add in more x's, the r squared will increase, but the r squared adjusted is a much fairer look at what's going on in the model. R squared adjusted does not have interpretation. It's just a penalized r squared. So this does not always need to go up. Which of these is the answer to the question of find the highest r squared adjusted? Which of these is the highest r squared adjusted? 1, 2, 3, 4, 5, 6. Which of those is the highest r squared adjusted? Which of those is the highest r squared adjusted? So you look through and you say, what's the highest r squared adjusted? That's step 1. Write these steps down. A lot of people make errors on this. Have them written down for the test. Look and say, okay, what's the highest r squared adjusted? 6. Boom. Click the wrong one. Anna, great job. 100 points, Anna, right there. 6 is the highest r squared adjusted. I want to see calculations of this in the chat. You got this. Step 2. Step 2. Subtract 0.005 from it. Standard. This is your standard now. Subtract 0.005 from it. Who can subtract 0.005 from it? I don't think you can. That'd be no, I wish. Well, you could. It reports to you a list, so you could store it and then sort it. There you go. So you could store it and then run it like that. So you could store it because it returns a data frame. I had a student who coded the way of doing this. We could code it too. He coded so it would tell him the answer every time. Nick, who got us the data camp. Nick coded it so it would just tell him the answer. He's like, well, I'm just going to code it so it tells me the answer. It's like, why should I do these steps if the code will do it? So what is the standard we're going to use here? I can tell you the answer, but I want you to tell me the answer. I'll write the equation, but I need someone to tell me the answer right here. Wait, 0.0. Correct. It's not 0.05. It's 0.005. And that usually confuses people because it's not 0.05 like p-value. It's 0.005. I think. Yes. Great job right there. Anna, crushing it today, Anna. Great work, Anna. That is correct. I was like double checking my brain. That is correct. So now, start with simplest and go up if they pass. Okay, now here is what we do. We want to use the simplest model possible. Does this, if they don't pass, Okay. Does this meet our standard right here? Yes or no in the chat. Does this meet our standard? We want at least this to use the model. So we're saying this is the best model, but we'll choose a model kind of close to it. We'll choose a model as long as it's this, because that's kind of close to this. That's the whole point of this. Being like, well, that's kind of close. I mean, they're basically the same. Does this meet our standard, yes or no? Does that meet this standard right here? Is that close enough to that? Is that standard? Does that meet it? Is that above that standard of r squared adjusted? Yes or no? No. What do we do next? We go here and we say, does this meet the standard? Yes or no? Doesn't. We go here and ask, does this meet the standard? It's not above it. And now, does this meet the standard? Does this meet the standard, yes or no? Does that right there meet the standard, yes or no? Double check, double check. Model number 4 is what we'd go with. Do you notice right here between, and I wish the graphic wasn't doing that. Come on, okay. Do you notice model 4, 5, and 6 all look very similar? Who notices how 4, 5, and 6 all look very similar? And if you look at the model metrics, especially with the R squared adjusted, they all look very similar. Does that make sense? Like 4, 5, and 6 are kind of very, very similar. So you can usually get an idea of what to go with by looking at the output. And right here, so here's the choose order output here. Oh, we didn't do not. Oh, I stored it. Oh, we don't want to store it. Let's view it. What is the answer to this question? If you're really good at solving it, you can solve it very quickly. And also the graphic kind of gives you hints a lot of times of which one to use. Take a second right here, see if you can solve it. I'll go through the steps, but which model would you use here? Which model are you going to use? I'll do the steps one by one, but can you solve quickly and be like, if we're going to fit something through this, we should fit a blank degree polynomial. See if you can get it. The graphic gives hints, like if you kind of conceptually understand that the models, if they have very similarity, we're probably going to use the ones that have the lowest order. But go through the steps right there. The steps are written out. Find the highest R squared adjusted. Subtract 0.05 from it. Nathan, you got it, man. Nathan's got there for 100 points. I'll go through the steps right here. Nathan is correct. Highest R squared adjusted is right here. So that's step 1. Subtract 0.005 from it. That's our standard. So with our standard, we say, is our first model meeting it? Is our second model meeting it? Yes, the standard is completed. Let's switch the variables again. This is practice right here. Which model are you going to go with right here? Which polynomial degree order? This one's another easy one. If you have this down, it's just like, boom, 3 points on the test. Which polynomial degree model would you go with right here? Looking at the output, it's clustered, so you can kind of tell what's going on with it. Pretty quick, you can get this one, but go through the steps. Doesn't hurt to double check. Which model would you go with right here? What do you think? Hunter is right. You're right, Hunter. It's number 4. Remember the steps. Find highest R squared adjusted. It's this one right here. Next step, subtract 0.005 from it, and that becomes your standard. Now be very careful. People start looking around. They say, oh, I'm going with this right here. If I say I'm going with this, what have I done wrong about the last step? I didn't start with the simplest. This does not meet standard. This does not meet standard. Does not meet standard. Does meet. You're basically trying to get the model that does the least amount of bendy stuff and saying, well, let's go for one that's simpler instead of the best. I know that sounds crazy, but you're just trying to make a model that's like good, but doesn't have to do too much bendy stuff. So right here, do we have another one? Number of phone contacts. Oh, wait, hours of sleep per night. Let me go to this. Hours of sleep. Number of hours of sleep per night. Your GPA with your tattoos. Now, this is interesting. Oh, right here. This is a tough one. Who knows the answer to this one? These are the steps for finding the correct polynomial order. Nathan, thanks so much for asking. Let me right here. This. Who knows the right one for this? This is a tougher one. Double check. I'm double checking my work too. It's a tougher one. Caught me a little off guard. I don't think it's 1. Why am I clicking on this one? Just for the moment. More on it later. Why am I clicking on this one right here? Why did I click on that one for the moment? I don't think it's 1. Pretty certain. Maybe I'm doing it wrong. Glad we did win that copy off guard. Not 6. Highest R squared adjusted. Correct. Tell me my next step. Tell me my next step. I just found the highest R squared adjusted. Tell me my next step. Go through the steps each time, just until you get it down each time. What's my next step? I just found the highest R squared adjusted. Subtract 0.05. That's my standard. Take a moment, pause right here, and tell me if you find the answer now. That's my standard of what I have to select the model. So now do step 3 right here. And step 3 says start with the simplest and go up if they don't pass. So do you know the answer now? Glad we do one that tricked people. That's the goal. That's the goal. It's not like a super hard thing, but just practicing. Not 6 though. Not 6. Not 6. Because I think people are starting on the wrong side of it. Good practice. Veda and Hunter, yep. Does this pass, yes or no? This is how we do step 3. Does this pass, yes or no? Does that right there pass, yes or no? This is how we do step 3. Does this pass our standard, yes or no? I'll do one more example because we don't have enough time for interactions. We're not doing interactions today. That does not pass. So I should check model 2. And does model 2 pass our standard? Let me double check. Let's go look at when the next assignment is. The next assignment is due. When is the next assignment due? Multiple regression, part 2. Activity, good activity. And then we have class next week. I think we've covered pretty much everything. And we've got the activity, so we'll be covering... Does it have... Let me go look at... We can go look at the file right here. Let's pull up the file. Does it have interactions? Because that's the only thing, and we'll be doing activity. I might do some activity tomorrow. Interactions. So the only thing we haven't talked about today. that is on, we need to talk about writing implicit lines and interactions, and everything will be covered then. So we're right here at the end. Want to do as many examples, but check it out. Choose order. Let's see, we're trying to make a model. Let's just do this real quick right here in class. We're trying to make a model to predict what's the very data set we're using. The data set we're using is the auto data set. So we need to load in here the data auto. And we are trying to make a model to predict, show me those variable names. We're trying to predict the fuel efficiency. So M save into LM, fuel efficiency explained by horsepower. We'll end class with this right here. Just got seconds. We're literally at the end. No, not survey 10 today. There's our model. Who here could tell me the proper polynomial for this model right here? We'll end class with this. Last question of the day, 100 points. Sorry, we're going to end right after this. Who can tell me the proper... This is your assignment. This is literally your assignment. Literally what we were just doing. Who here can tell me the proper polynomial order for this model? I'm taking a moment myself. This one might be a little... Ooh, it's so close. It's so close. That's a tough one. Very close. Ending here in like 30 seconds. It's very, very close, Kevin. It's very, very close. Select your highest R-squared adjusted. Subtract 0.005. And there's your standard. Does that meet it? Does this meet the standard? Here's the standard. Does this meet it? Does that meet the standard right here? So the answer is 4. 4 was the highest, and this is just barely outside the standard. It's barely below the standard. Below the standard, below the standard, below the standard, above the standard. Does this make sense? That's the end of class right there. Sorry, I went just a minute over. But do people have confidence, especially for those questions right there, where you're just going to switch the x variable and find out the polynomial order? And then we'll talk about, it shows you then how to fit it, and it is in the notes how to fit the model using the poly function on the variable itself. Don't worry, Kevin. 100 points right there, Kevin. Kevin, I'm throwing you all the point buttons right there. Makes sense? Yes, just practice. Don't worry. Just make sure, just write it down, look at it, and then just do it like a robot. That's how we do things here. Just make sure to, like, very careful. And Kevin, you're so close to that top tier. You got this, Kevin, man. Great work. It's all about that practice. That way, when we get to the test, we're like, okay, we find the highest R-squared adjusted, we subtract 0.05, and then we find the one, we go up in order until we meet the standard. I think it's got it. Well, great work, everybody. We're going to be doing some activity. I guess we might do it. Oh, I have a going back to come back next class with a function to find this thing. Yeah. So actually, wait, here, let's do it. Let's do it. Let's go do that. Here, wait, who wants to code that function real quick with me right here? I bet you know what we could do. I bet you we could code that function in 5 minutes. I need to grab a little food between classes too. Let's code. You know who we need for this. You know who's going to be here for this. It's time for a little Stats 1 Hacker Man. He hasn't appeared in a while. Let's go code this function. Let's use the choose order. Choose order right here is going to run our model. And there's the list it returns right here. X1, X2 for the extrapolation. Those are the X variables we are using. So the further out we are on the X axes, the more we are extrapolating the model. Because extrapolation only occurs on the X's. I have a question about the points. Yeah, feel free to ask. Yakui, feel free to ask. So we have our list right here. And now we want to go to this and find from the list. Let's store it as a data frame for a moment. Data frame, inside the data frame, we're going to take the second. There we go. And now let's take the max. Let's go max of this. There's the maximum value. Subtract 0.05 from it. There's our standard. Yeah, you're doing it. Yep, you're doing max. You're doing exactly what I'm doing. But how can one X variable be two-dimensional? Oh, but remember we're doing multiple X's. So in our model, there's multiple X's. We're in multiple regression. So you have X1, X2, X3, X4, X5, X6. So there's a multiple X, because we're doing multiple regression. Simple regression is just how far are you on one X. Multiple regression is how far are you on your multiple X's. So now we need to go data frame $2, and then we need to find the first true. How do we find the first true? Well, this should do it right here. So this finds the ones that are greater than the standard. Does that make sense right here, Max? Like this is the first one right here. So we want the first true. I'm just thinking how to return the first true. So you know what we could do? We could say, we could do a which right here. So we go which on this, and this gives us the positions of the true. We then use this in our data frame to only return, those that we need rows, not columns. So we return the rows of the trues, and then guess what we do? We go here and we say data frame $. Oh no, this is the new data frame. So let's say new df, and the new data frame, we just go to the new data frame and we take from it the order of the first one, and then we say paste or cat paste use order, and then we say this right here, use order 4. And so basically I made a new data frame of only the ones that meet the requirement. And so now let's check this out. We're going to take all this, go into a fun, and the only thing it needs to take is model M right here, which will be used throughout. Let's say choose order advanced, and there's the choose order advanced, and here's choose order advanced. So we do this, and literally our questions on our assignment now. Check this out. Remember this whole assignment thing we were doing? The auto data set. I shouldn't do this, but I'm gonna do it anyways. Watch this. You see how it has these different X variables in here? We could do something even better. But cab volume. There you go. Use order 3. Horsepower. Use order 4. Top speed. Use order 2. Weight. Use order 4. I'm not saying those are the answers, but I wrote a function that did everything for me. So does that make sense, Max, right there? And Yaku, do you have a question on the points? Feel free to ask those questions, but I'm not saying that's the answers, but you always get some extra hints in here. Can you do does this make sense, Max, and everyone? Like what we've done right here, so extrapolation requires multiple extra. Extrapolation could be on a singular X. So you were able to assume it's one row. Exactly, because in the new data frame I calculated, the new data frame already has them ordered. So you think, okay, cool. The new data frame already has them ordered. So when I created the new data frame, it's only the ones that meet the requirement. And since it's from the original data frame, they're already ordered. So I went and just took the first one of the new data frame. So when I made the new data frame, it's only the ones that meet the standard, which I guess, yeah, this is the code right here. I took this right here actually. So yeah. So I wrote this right here, which takes only the rows that meet the standard. Does that make sense? So these are only the rows in the original data frame where the things meet the standard. The which returns the positions. So hence I have this in the row space right here. Does that make sense, Max, right there? This right here is the positions that meet the standards of the original data frame. So we're looking at, here's my standard. Here's the values of the R. Says disconnected. Reconnected successful. There was a real quick disconnect. Yeah, so this does it all right here. Pause the screen and copy it down for yourself. Does RMSE and typical miss the model mean the same? Are they the same number? Correct. That is correct. RMSE is the same thing as typical miss. I can say that directly right now. RMSE and typical miss are the exact same thing. That is very, very correct. Well, that's got it. But no, just writing your own functions can really help because you could use this for any sort of thing you want right here, whether it be like your height, weight stuff. And if you run this right here, which one did we say for this? It says use model 4, and you could literally check your output right here. And we could also do a return. So we could do return on the choose order. And if I do a return on the choose order M right here, it should return also the output. So choose order advanced also, that'll end the function. I want to put this on a new line. It should be in the cat then. Let's see if Brian knows how to do his stuff. There we go. So look right here, it says use order 2. So whenever I run this, it's now going to tell me which order to use. You're welcome. And this is really the power of coding, because now it just tells me which order to use. It literally does. I could also say the standard was this, this one has this. I could write everything in here. It's just going to report for me. I have it as a new line, but my choose order advanced function now just tells me which one to do. Not the same question. It could. Yep. Important to know. Important to know those things are the same. Good stuff right there. Excellent questions. And just, I don't know. I love writing functions. It's fun. I remember when Nick did this, I was like, that's so cool. And it's still cool. But now I'm just like, oh, it's not, I don't know. He did it during like one of our first semesters teaching 320. And I was like, we can do this. We got this. Well, with that, we'll be back. If you love coding, if you like writing functions, if you like making life easier. Oh, you're welcome, Scotty. Excellent work right there. Well, we got it. We got our choose order advanced function. So it does all the work for us. That starts a new line without the, great question right there. Without the \n, it'll combine these words right here. Do you see how this looks right here? The \n is a special character. So this is a new argument in the cat paste. Cat paste is so that it prints to the screen but doesn't do it. I'll check out the question on Discord. Yep, and I'll do it between classes or after classes probably. About the points on YouTube. Yep. So the points on YouTube get added to your final grade. This might answer the question. You can check your points anytime with !points. It's added to your final grade. !point. Mubot will tell you your points. And at the end of the semester, those are points added to your final grade. You also get Discord points by talking in the Discord chats. And Mubot's always here, hanging out, giving out those extra points. I am right about to almost 1,000 hours streaming online. I've got 374,000 points. Man, I'm getting a lot of points. With that, we'll be back. I'm going to go grab a quick snack between classes. So say hey, check out your points. Talk to everyone later. Bye for now. Bye.